Welcome students to the 14th lecture on Introduction to Fuzzy Sets, Arithmetic and Logic. In the last few lectures, we have been dealing with alpha cuts of fuzzy sets. Now, you may ask why alpha cuts are so important with respect to dealing with fuzzy sets. One major advantage of alpha cuts is that the sets induced by them are all crisp sets. Therefore, the advantage of alpha cuts is that many properties and operations of crisp sets can be extended to fuzzy sets with the help of alpha cuts. And any such property of crisp sets that can be extended to fuzzy sets with the help of alpha cuts is called a cut-worthy property. We have seen in our earlier lectures that convexity is a cut-worthy property. Also, we have seen that different arithmetic operations can be extended to fuzzy sets with the help of alpha cuts. Now, alpha cuts have another advantage, and that is that each fuzzy set can be uniquely represented by its alpha cuts, and these corresponding things are called decomposition of fuzzy sets with the help of alpha cuts. So, in today's lecture, we shall focus on representation of fuzzy sets using alpha cuts. So, let us first consider for illustration a discrete fuzzy set say we call it x and it is 0.2 by x 1 plus 0.5 by x 2 plus 1 by x 3. That means, we are looking at one fuzzy set consisting of only 3 elements x 1, x 2, x 3 and these are their corresponding membership values. Now, let us look at different alpha cuts of x. For example, we consider 0.1 cut of x, which is going to be, we know that all x 1, x 2 and x 3 be there, but we write it using their say cardinality. We can write it as 1 upon x 1 plus 1 upon x 2 plus 1 upon x 3. Similarly, 0.2 alpha cut of x is equal to, we know x 1 comma x 2 comma x 3 and that also we can write it as 1 upon x 1 plus 1 upon x 2 plus 1 upon x 3. What is 0.5 alpha cut of x? This we know that it will comprise only 2 elements x 2 and x 3. Therefore, we can write it as 0 upon x 1 plus 1 upon x 2 plus 1 upon x 3. And let us consider one cut of x, which consists of the singleton x 3 and this we can write it as 0 upon x 1 plus 0 upon x 2 plus 1 upon x 3. So, I hope you understand the construction. Now, with the help of the alpha cuts, we can construct another set of fuzzy sets as follows. Let them call alpha A. I am putting the alpha as a subscript here on the left hand side. So, you should not confuse this with alpha cut of A, because this is a crisp set, but this is a fuzzy set, and the membership of x in this alpha A is defined as alpha times alpha cut of A of x. Therefore, we find the following. Say 0.1 of A, this is going to be 0.1 times 1 upon x 1 plus 1 upon x 2 plus 1 upon x 3. You can find that we have found that 0.1 x 1 is 1 upon x 1 plus 1 upon x 2 plus 1 upon x 3, and therefore, this we can write as 0.1 upon x 1 plus 0.1 upon x 2 plus 0.1 upon x 3. Therefore, the fuzzy set 0.1 A is basically this. In a similar way, therefore, 0.2 A is going to be 0.2 of x 1 plus 0.2 by x 2 plus 0.2 by x 3. 0.5 A is equal to 0 by x 1 plus 0.5 by x 2 plus 0.5 by x 3, and 1 A is equal to 0 by x 1 plus 0 by x 2 plus 1 by x 3. Now, let us consider standard union of these fuzzy sets, and by standard union we mean maximum of the membership values. Therefore, union over alpha A, if we consider, then we get the maximum membership value that we got corresponding to x 1 is 0.2 plus the maximum membership value that we got corresponding to x 2 is 0.5 and the maximum that we got corresponding to x 3 is 1. Therefore, now if we compare with the original set, we get that, okay, I call it x there. So, we get that we get back the original set. Or in other words, x is equal to union over alpha x for all alpha between 0, 1. So, the above observation is true for all fuzzy sets finite or infinite. The above observation, when we extend to infinite sets, then instead of maximum, we consider supremum of all the membership values for each element x I to alpha A for all alpha belonging to 0, 1. This leads to different theorems for decomposition of a fuzzy set into with the help of its alpha cuts. So, let me now state the different decomposition theorems and I give proof for them. First decomposition theorem. It states that if A is a fuzzy set defined over X, then A is equal to union union over alpha of alpha A, alpha belonging to 0, 1. So, proof, let us consider any x belonging to x. Then let mu A of x be equal to A, which belongs to 0, 1. So, we have a set x, we have defined a fuzzy set on that crisp set x by assigning some membership functions, and let us consider any particular element x and let its membership value to the fuzzy set A be small a. We shall show that the membership of x to the union over alpha of alpha A is equal to A, and therefore, what will happen? Because this x is arbitrary, therefore, if we can show that its membership to the union of this alpha A is also A, then we can show that for all x, whatever is its membership function to the fuzzy set A will also be same as the membership to this union of these fuzzy sets. Therefore, this union of fuzzy sets is going to represent the original set A. So, that is the motivation. So, we prove as follows. Now, what is mu union over alpha, alpha A of x? Since we are in a general domain, so instead of max, we are considering supremum. So, this is equal to supremum over all alpha mu alpha A of x. Now, this we divided into two parts is equal to maximum of supremum over all alpha belonging to 0 comma A mu alpha A of x and supremum over all alpha belonging to A comma 1 mu alpha A of x. I hope you understand the mathematics. So, this alpha actually belongs to 0 comma 1 and A is given to be the membership of the element x in the fuzzy set A. Now, this range of alpha we are splitting into two parts, one is 0 comma A closed and other is open A to 1. So, our aim is we will calculate these two different supremums and whichever of them is maximum, we are going to call it the supremum of all alpha between 0 to 1. So, the logic is clear. Now, supremum over alpha belonging to A comma 1 mu alpha A of x is equal to 0. This is because since mu A of x or membership of x in the set A is equal to A, x does not belong to alpha cut of A when alpha is greater than A. This we have seen. Therefore, for all of them the alpha times alpha cut of A is going to give you 0 for this x. On the other hand, supremum over all alpha belonging to 0 comma A mu alpha A of x is going to be supremum over alpha belonging to 0 comma A of alpha, because this x will belong to all the alpha cuts. So, when you are multiplying it by the alpha, the corresponding membership to alpha A is going to be alpha, and now I am taking supremum of them from between 0 to A, and this is going to be A. Therefore, mu of x to the union of alpha A is equal to A is equal to mu A of x. As I said, since x is chosen arbitrarily, therefore, this proves the theorem. So, example, let us consider the TFN, the triangular fuzzy number 1 to 4. So, how it will look like? Suppose this is 1, this is 2 and this is 4. Okay. So, this is 1 and the membership function will look like this, that we have seen many times. So, this is going to be the shape of the membership function for the triangular fuzzy number. Therefore, what is mu A x? Mu A x is equal to x minus 1 if x belongs to 1 comma 2, and this is going to be 4 minus x upon 2 if x belongs to 2 comma 4, and it is going to be 0 otherwise. Okay. So, let me draw it again for your better understanding. Suppose this is 1, suppose this is 2, suppose this is 4, and we are talking about this triangular fuzzy number. Therefore, for any alpha, this is going to be the alpha cut. So, what is alpha cut of A? Alpha cut of A is 1 plus alpha comma 4 minus 2 alpha, and therefore, mu alpha A of any x is equal to alpha if x belongs to 1 plus alpha to 4 minus 2 alpha and it is 0 otherwise. So, for example, if this is my alpha cut, then all these elements are belonging to alpha cut of A, and therefore, in the alpha cut their membership is 1. Therefore, when we are multiplying this by alpha, for all of them this is going to be the membership. If we take any alpha prime which is less than alpha, then we see that the corresponding alpha cut is this, and for all of them the membership is, for all of them from this interval to this interval the membership is alpha prime, but for all this x here the membership is alpha. If we understand that, then it is easy to observe if x belongs to alpha cut of A, then x belongs to alpha prime cut of A as well, when alpha prime less than equal to alpha. Therefore, all these x will also belong to this. However, if I take a beta which is above alpha, then we can find that only these are the elements which belong to the beta cut of A, and there they will have the membership value equal to beta. Therefore, what is the membership value for each x in the union of alpha A? If we consider this x, we can see that as alpha increases, we are getting alpha, the value of the membership to be alpha, and it goes up to this point, which is its membership value say A, and which is its membership value, and therefore, above that it is not member of any of these alpha cuts, therefore, it is 0. Hence, its membership value is going to be its membership in the original set A. Similarly, if you give me any arbitrary x, I can see that its membership to the union is going to be the supremum of all of them, which is equal to this, and which is nothing but its membership value to the original set. So, this example illustrates how you can decompose one fuzzy set with the help of its different alpha cuts. Now, let us talk about the second decomposition theorem. This theorem suggests that for every fuzzy set A defined over a set X, can be decomposed as follows. A is equal to union over alpha, alpha plus of A where alpha plus of A is defined as mu alpha plus of A of x is equal to alpha times alpha plus cut of A. Let me put a mu there x. That means, that is, if x belongs to alpha plus cut of A, then mu alpha plus of A of x is equal to alpha, and if x does not belong to alpha plus cut of A, then mu alpha plus A of x is equal to 0. Let me illustrate. Suppose we have point 1 x 1 plus 0.3 x 2 plus 0.7 x 3, and let us call this set to be A. Therefore, point 0.05 plus A is equal to 1 by x 1 plus 1 by x 2 plus 1 by x 3. But point 1 plus A, point 1 plus cut of A is equal to 0 upon x 1 plus 1 upon x 2 plus 1 upon x 3. So, basic difference is that since we are taking strong alpha cut, any x which is having membership value alpha in the original set A will now have 0 membership to 0.1. It will have 0 membership in the strong alpha cut of A. Therefore, 0.1 times 0.1 plus A, which will give us the set 0 by x 1 plus 0.1 by x 2 plus 0.1 by x 3, right. Now, let us consider any alpha belonging to open interval 0 to open interval 0.1. For all this alpha, we will have alpha plus cut of A is equal to 1 upon x 1 plus 1 upon x 2 plus 1 upon x 3. Therefore, we can say for all alpha belonging to 0 comma 0.1, alpha plus cut of A is equal to alpha by x 1 plus alpha by x 2 plus alpha by x 3. But for all alpha belonging to 0.1 to say 0.3, we shall have alpha strong alpha cutoff is equal to 0 by x 1 plus alpha by x 2 plus alpha by x 3. This is because mu a of x 2 was taken to be 0.3, but for alpha greater than equal to 0.3, we shall have for x 2 mu alpha a of x 2 is equal to 0. Similarly, we can illustrate for x 3. If we observe that, then we can formally prove the theorem as follows. Let mu a of x is equal to a. Therefore, mu union over alpha a of x is equal to supremum over alpha mu alpha plus a of x, which we can now write it as maximum of supremum over alpha mu alpha plus a of x, x belonging alpha belonging to 0 comma a and supremum over alpha, alpha belonging to a comma 1 mu alpha plus a of x. So, notice the difference. In the earlier example or in the first decomposition theorem, we had a closed bracket here, but since in this case closed bracket A implies that membership is going to be 0 for the corresponding x, we put it on this side. Therefore, as before, supremum over alpha belonging to a 1 mu alpha plus a of x is going to be 0, but supremum over alpha belonging to 0 comma a mu alpha plus a of x is going to be limit alpha going to a of alpha, which is going to be a. Hence, mu of union over alpha of alpha plus a of x is equal to a is equal to mu a of x. So, this proves the theorem. There is a third decomposition theorem This is defined in terms of level set of the underlying fuzzy set A. Now, you may ask me what is the level set. So, let me explain this concept. We know that we can have alpha cut of A for all alpha belonging to 0, 1. In fact, it can be 0, 1 because there may be elements having membership 0. But it does not mean that all alpha cuts are different. For example, if A is equal to 0.1 x 1 plus 0.3 x 2 plus say 0.7 x 3, then for all alpha belonging to 0, 0.1, we have the same alpha cut, namely x 1, x 2 and x 3. The level set lambda for a fuzzy set A is the set of alpha for which we have distinct alpha cuts. So, formally the level set lambda of A is equal to the set of alpha such that mu A of x is equal to alpha for at least 1 x belonging to A. Therefore, in the previous case, lambda A is going to be only 0.1, 0.3 and 0.7. So, the third decomposition theorem states that for every fuzzy set A, A can be decomposed as A is equal to union over alpha of alpha A, where alpha belongs to lambda A, where u is in terms of standard union and lambda A is the level set of A. Okay, students, I stop here today, but before I go, I give you some results and I ask you to prove yourselves. One is that for any fuzzy set A defined over X, we have the following. Alpha cut of A is equal to intersection over all beta less than alpha, beta cut of A, and it is same as intersection over all beta less than alpha, beta plus cut of A. In a very similar way, we can have alpha plus cut of A is equal to actually union over all beta greater than alpha, beta cut of A, and which is equal to again union over all beta greater than alpha, beta plus cut of A. So, as I said, I want you to try proving this with the concept of supremum and infimum. The proof will be very similar, that is why I am not doing that in this class. I stop here today. In the next class, I shall talk about another important concept of fuzzy set, which is called extension principle. And what is extension principle? We have functions defined over crisp sets to crisp set. What happens if we impose a fuzzy set on those crisp sets? Then how are you going to extend the function so that they can be defined from a fuzzy set defined on the crisp set X to another fuzzy set, say B. Extension principle helps us to define those fuzzy functions or define those fuzzification of those crisp functions when we are thinking in terms of fuzzy sets. Okay, that is for the next class. For the time being, let us stop here. Thank you.